Nesting. Who can remember anything about nesting?
It's one inside the other there. Yeah, within the students within the
Tupperware nesting. Right? So classrooms within schools, within districts, right? When you have situations that have other factors that influence the between group differences, then that's nesting is a technique that can kind of get rid of some of that variance or control for it. Treatment by blocks, that was one where we had big variability in the DV, and we wanted to kind of redo it by blocking them into like high, medium, and low, severe, moderate, something like that, to take away some of the within-group variance.
That's when it creates a new IV.
To create a new IV, exactly. So in ANOVA, where you just create a new IV, but it's a funny IV, it's one where you know that it'll be significant because you're creating it that way. But again, it's a technique to reduce within-group variance. So another way is to just put in additional IVs, just anyway. But now we have a little bit more sophisticated technique called analysis of covariance, which is used to achieve statistical control of error when experimental control of error is not possible. So even if you have random assignment, you still may have a lot of error from some other source within your data that creates too much within-group variance, and that creates type 1 error, type 2 error, right? So you're not going to get significance between the groups because there's too much within-group variance. So we're trying to cut down, remember where we started at the beginning of the semester with within-group versus between-group. We can kind of cut down that within-group variance. We can get more power to get a significant difference. So another way you can do that is through analysis of covariance by combining regression techniques with ANOVA techniques. You can take some of the variance out of that within-group variance. It reduces the estimates of experimental error, but it also adjusts treatment effects with respect to the covariate. So if the covariate might have some influence on the means, it'll correct for that by doing something called adjusted means. And they're adjusted for the covariate. So in random controlled trials, reduce within-group variance if the CV is correlated to the DV, right? So if the covariate is not correlated to the dependent variable, you're just losing a degree of freedom. You get nothing out of it. The covariate has to be correlated to the dependent variable for them to be useful. In static group or quasi-experimental designs to correct for existing between-group differences. So this is a little trickier use. So let's say you're comparing 3 different eating disorder groups to one another on attachment history. You get about 12 of those dissertations a year, some kind like that. And because you're pretty sure that bulimics and anorexics are more compromised attachment history than obese people or something. So you have a measure of that. Well, the problem is that those are fixed groups, right? You're not randomly controlling. You can't randomly control someone to bulimia versus anorexia versus obesity. So the groups have all the characteristics inherent in the group that could be the reason for the differences in attachment history, right? May not be the reasons that you really want. Maybe the bulimics are just have more psychopathology so that they report more attachment disturbance than the other groups. So trying to get rid of that problem with ANCOVA is something people do, but it's a bit problematic because you never know for sure you're not really throwing the baby out with the bathwater or whether you're really getting a good way of controlling for those other factors. Nevertheless, it's done a lot. When people have fixed groups, and sometimes it's the only way you can study things, you're going to be essentially doing a correlational study, and people are going to question, how do you know the differences between these groups really were the eating disorder diagnosis, but it wasn't that one group had more single parents, that one group had older moms, that one group was more abused than the other group, something that was different that might affect attachment history that really isn't what you care about, right? So those are problematic when you're trying to do these quasi-experimental designs or static group designs. Another use of it is, which we won't use, is an alternative to repeated measures ANOVA. So in the old days, people don't do this much anymore, but if you had a repeated measures ANOVA, so you had a pre and a post test, what you could do is use the pre-test as a covariate for the post-test, right? So then you're saying, okay, I'm using a regression to make sure that the post-test is independent of the pre-test levels. And then I just do a straight ANOVA on the post-test. So if I have, group A, group B, and I have pre, I have post, here's the pre-scores. I could covary out the pre-scores from the post-scores and then just compare them. Then these two would be compared essentially on the residual of the regression. Whatever part of that score is independent of the pre-score would be what I get here, and I can just do that straight comparison. And you will see that from time to time. The disadvantage is you get adjusted post-test scores, so you don't really see what happened from the beginning to the end. So if people started higher or lower in one group, you don't see that. They're adjusted for the pre-score. So rather than get a nice graph like this that we were working with last semester, where one group went up, one group stayed the same, all you're going to get is this difference controlled for wherever they started, which sort of disguises some of the effect. However, you will sometimes see that. We won't do that, but we'll sometimes see it. And later we'll talk about ANOVA and Mankova in multivariate analysis covariance, which is the most complicated thing that combines everything we've done for the whole year. There is a way of kind of taking variables and knocking one off and knocking another one off and seeing how much it changes from time to time, essentially using analysis of covariance. But don't worry about that one yet. I'll talk about that later. Most experiments, the scores of the covariate are collected before the experimental treatment, like pretest scores or exam scores or IQ scores or some history of something. Some experiments, the scores of the covariate are collected after the experimental treatment. Sometimes afterwards you find out if there was high anxiety, motivation, SUDS ratings, things that sometimes it's not as good to be after. It's important to be able to justify the decision to collect the covariate after the experimental treatment, since it's assumed that the treatment and covariate are independent. So after you've done the data analysis, then you go in and say, oh, well, I think all these people differed on this one. I'm going to use that as a covariate. That's a lot shakier than having it as a covariate to start with, where you know that there's going to be a problem. So the way it works is analysis of variance and variability is divided into two components, experimental effect and error, just like we did before, like we showed up here. In ANCOVA, we get a new thing. We partition it into three components, the effect, the error, and the covariate, which is taken out of both the effect and the error. We're partitioning it out of both as a way of controlling for some other factor. Covariate scores are available. We have information about differences between treatment groups that existed before the experiment was performed. ANCOVA uses linear regression to estimate the size of the treatment effects given the covariate information. Uses regression. The adjustment for group differences can either increase or decrease depending on the dependent variable's relationship with the covariate. So sometimes you might get significant differences just by themselves. When you put the covariate, they go away. Sometimes the covariate makes them bigger, depending on how it works, just how the correlations actually work. So you don't know exactly how it's going to go until you actually do it. Between group analysis of variance, the error variability comes from the subject within group deviation from the mean of the group. It's calculated on the basis of the S within A sum of squares, like we did last semester. So we kind of look at variability that way. But in ANCOVA, we use a regression. The residual sum of squares is based on the deviation score from the regression line instead of from the mean. Residual sum of squares will be smaller than the S within A of the sum of squares. This is how ANCOVA works. So let's go back through that again. So last time we looked at the variability from the mean, every individual from the mean. But now we're going to throw in a new twist and say, okay, we're going to look at it from not the mean, but the regression line between the CV and the DV. Excuse me. So then we kind of get rid of that slope. We factor in the slope of the relationship between the covariate and the dependent variable. And that should produce lower within group variables.
Is the covariate kind of like a mediator?
No, it's more like a moderator of anything, but it isn't really either of those. Just another factor. I'll give you some examples. And we have a couple of new assumptions here that we'll go through that are a little complex. So we have our usual big three: normality, homogeneity, variance, and dependence of observation. Those still hold. Now we have a couple new ones. Linearity refers to the relationship between the CV and the DV. That's a scatter plot between them. So the covariate is a variable that correlates with the dependent variable. We want to see what the relationship between those is. And we're assuming that it's linear, not curvilinear. And COVA doesn't work if it's curvilinear. The covariate is supposed to have high reliability of measurement. If it doesn't, it kind of is an assumption violation. And the new one that's a little more complicated is called homogeneity of regression slope. What that one is that the relationship between the CV and the DV remains the same for each level of the IV. The relationship between the CV and the DV remains the same between each level of the IV. So if you have three groups, you look at each group separately, you look at the slope of the covariate to the dependent variable, you're assuming that the slope is about the same. In other words, if something relates to the DV, it relates about the same each way. So let's look at some examples. I've said those already, I think. Linear regression is used when the true regression is curvilinear. That includes. So those are the scatter plots: covariate versus the DV, covariate versus the DV for group A, for group B. But now what happens if in group A and group B you don't have that? That's another version of heteroscedasticity. See how the slopes are different in the two? So we're going to test to see that those slopes are the same. We're going to actually do it with a real example in a second.
You're seeing one graph with the other.
Yeah, you're going to compare that. We're going to get the computer to compare one slope to the other slope. So that's just a little more detail. We can test this assumption, but we'll show you how to test that assumption. Some tricks to it. All right, so a couple examples before we get to our main example. Researchers looking for performance on crossword clues. Subjects have been grouped into three vocabulary levels: high, medium, and low. ANOVA and Tukey's in this data find that the high group and the low groups are different. So you do a straight ANOVA on that, okay? However, the amount of experience in solving crosswords might make a difference, right? So there might be a relationship between experience with crossword puzzles and your ability to do them. Plotting the scores against the age, we obtain a graph. So we see, okay, older you are, the better your performance. And it's the same for high, medium, and low, but they all have the same slope, but they do differ from one another independent of age. So if age is mixed into those, it just comes in as error. Right? So if you don't control for age is just the source of error there. So now we're going to be able to kind of tease that out. From that, we're going to get two elements: adjusted or estimated means, significance, testing significance of the covariate, and testing new assumptions. And there's an article that warns you about all the terrible misuses of COVA. In case you're ever actually doing one, you'll have this graphic in the back and we're not going to worry about it right now. There's a million. This guy makes you feel like nobody should ever do COVA, but there are some good news. So the example I chose for today is from this other book by Andy Fields. It's comic one. Thought we could use a little levity thing. And the problem is you're testing the DV is the libido of the subject. The independent variable is 3 doses of Viagra. Low, medium, and high. So in the initial analysis, we just do the straight ANOVA, the way we usually do, and find that there's a difference in libido with the 3 levels of Viagra. Pretty obvious. But then it occurs to the researcher that maybe the libido of the partner might have an influence on the libido of the subject. Right? So I guess it's the Viagra. I guess the subjects are all males, and the partners, I think, we'll assume the partners are female. They don't have to be those. Could be either one. So if we thought that was the case, we would think that the partner libido might have an influence on the data, both within group and even adjusted the scores. So we wanted to control for the libido of the partner and still do the comparison of the 3 doses of the drug. We could do that with an ANCOVA.
Can you say that one more time?
Yeah, so we want to know whether there's a difference in the dosage levels, but we want to control for the libido of the partner, because that is not going to be what we really care about. We want to know if the drug works independent of other factors, right? So we'd like to hold constant, and you can imagine that the libido, the willingness of the partner to engage in sexual stuff, has something to do with the libido of the person themselves. That's his premise on this one. He comes up with these wacky little examples. All right, so doing them is pretty easy. You just use general linear model, univariate. Libido is the DV, the dose is the fixed factor IV, and the partner's libido is the covariate. Just have one more thing to put in. We have our usual suspects for options. First 3 on the left, top one on the right. Get the means. Make sure you always get the means in this one, because those are a special kind of mean. You can do post hoc tests just as well as always. Here we're not bothering with it now. You can do a plot. It's a simple plot. So this is nothing very new that we haven't done. Just putting one more thing in the box. Everybody go okay with that so far?
What did you put under covariate there?
The under covariate was the partner's libido.
Okay.
And I gave you the output then. So here's what the output looks like. So a few little things to note here. The first thing are the unadjusted means. So those are the means of the placebo, low dose, and high dose. And their standard deviations. You can see here it doesn't have even sample size here either. They're slightly different. The Levine's test is the same as we're used to. It's the test of homogeneous variance, but significant biological homogeneity. But the output here is a little different. As usual, we ignore corrected model and intercept. But the doses are main IV. Right, see that? And it's significant with a decent effect size. 0.016. So that means there was a difference between the dosages, even controlling for partner libido. Now, did partner libido have an effect? Well, that one you test by looking at whether that's significant by itself, and it is. So that line doesn't tell you anything about dosage, it just tells you whether the covariate is significant. It's important for that output. All it tells you is the covariate significant.
Which one?
So this 0.02 tells us that the covariate was significant. There was a significant correlation between the covariate and the dependent variable. Significant for a covariate means the correlation is not zero. We're 98% sure that the correlation is not zero.
Between covariate
And
and
the-
covariate?
And the DV, CVDV. Okay, so the ANCOVA worked. I should do the ANOVA without it. You can see the difference. I'll do that in a second. So remember what these significance levels are like. They also give you something new, which is what's called estimated marginal means. Those are the adjusted means. So remember, if we look up above, look at your data above for the unadjusted means, you'll see these slightly differ. So 3.22, 4.89, and 4.85 versus 3.31, 3.07, and 5.920. So that one got a lot bigger. So these are the means of the dosage levels independent of the partner libido. With that parceled out.
Can you repeat that?
And those are the means of the three dosage levels independent of the partner libido, independent of the CV. And they're adjusted so that we now have a mean that we think means something without, once we've controlled for the CV. So we've now controlled for the CV, just like we do in regression.
So this is all about reducing error.
It's mainly about reducing error, but it also does make some adjustments to the means, which means we have a more accurate way of assessing the IV. And if you look at the data, you can see that the big difference there was between the high dose. The low dose didn't do any better than the placebo doesn't look like. It's actually a little worse maybe. And the high dose was a lot higher. And that graph is of the adjusted means. Sense? So you can think of other more salient examples for us. If you were comparing three treatments for PTSD, let's say we're doing exposure with some somatic component, and support groups for three treatments for PTSD. Let's just say for now we're going to look at the outcome scores without the pretest scores. It gets complicated to do pre-post with covariance, so we'll just leave that aside for now. So let's say we have improvement scores for three groups. These are exposure therapy. This is exposure plus some somatic therapy like yoga or biofeedback. And this is the support group therapy. And these are percent improved scores. Okay, can anybody think of any possible covariates that we might want to look at for that?
So what are the categories? Support?
Exposure plus somatic, and just support therapy. So we're testing three different kinds of therapy for return vets with PTSD, let's say.
Intrusive thoughts could be something. Like intrusive thoughts.
Thoughts?
Intrusive thoughts.
Intrusive thoughts. Okay.
quantity of traumatic incidents?
Okay, yeah, so what? So
Quantity of traumatic incidents?
okay, how about, there's another scale called the combat experiences scale, in which the vets are asked check things that happened to you in your deployment. I witnessed a buddy getting killed. I was affected by an IED. Somebody that I trusted, an Iraqi that I trusted, turned out to be a member of Al Qaeda. A whole bunch of those. So you get a score out of that. Those are good scales because the vets usually fill them out fairly honestly. They don't fill out symptoms honestly, but they do fill out events honestly. So now, why would that be relevant as a covariant?
Probably correlate the number of traumatic events they have, probably increase the severity of them.
Yeah, so that would be true, but why would we care about that for us? So let's say we're trying to see if there's a difference between these three therapies.
Maybe someone with more severe symptoms would be better suited to.
Exactly. What if the therapies interact with the combat experiences so that there's a lot of error within these groups that have to do with their combat experiences, right? So we get a lot of in-group error in terms of how well they respond to the therapies because of those combat experiences. It would be nice if we could control for that. So essentially, we statistically control for combat experiences and then get a purified score to compare. That would give us a little better idea, possibly, how it worked. Now, if combat experiences didn't correlate with how much they improved, then it would be a waste. But it's pretty obvious that mostly they probably would, right? We know already. Or the number of, remember the other study, the number of intrusive thoughts and dissociative experience, dissociation. Another one might be dissociation. Another covariant might be dissociation, right? How much dissociation did they experience after the trauma? Remember we did that one, that was real data, but we have a dissociation experiences scale. Ask questions like, after your event, did you find yourself places and you don't remember how you got there? Did you find that you're getting spacey a lot after the event? Things like that are kind of dissociative symptoms. So those symptoms might have been listed. No, you'd think that probably, in fact, we know from previous literature that high dissociation really is a very powerful impediment to good exposure therapy, right? Because what happens to those folks is the minute you expose them to their trauma scripts, they dissociate, making progress.
Would another potential one be like when we were discussing the Holocaust survivors, something like a hardiness rating?
Yeah, could be. Although usually that would not be a nuisance variable as much as what would be the comparison now? You're comparing.
I guess I would maybe expect a little bit of difference depending on their kind of hardiness in whether.
What's the IV though?
Okay.
So you'd have to kind of decide what the IV is. But I mean, if the IV was age of death. Okay, so we're going to compare. Let's say we're going to compare World War II Holocaust survivors to Balkan to the Balkan War survivors of slaughters and all this stuff versus something else, and we wanted to see if the three of them had impaired. Usually, those kinds of experiences short people's lives pretty regularly. People who have been through the slaughters in the Balkans have shorter lives. The Holocaust have shorter lives. Lots of trauma.
I was just thinking, I guess, that the IV would be I'm sorry.
And usually if we were doing hardiness, we'd be more interested in that as kind of another IV problem. We want to know if hardiness affects those.
Okay.
We wouldn't want to get rid of it probably.
I see.
So that one might not work so well.
So covariant is a nuisance variable.
Well, a variable that you want to control. You want to control to get rid of it usually to reduce within group variance, but also to make some adjustments in the means. So in this case, I think that would be a good example of that, because we don't really care that there's, we're hoping that the combat exposure scale is equivalent among those three groups. It very well could be random assignment to these three. So we could come in to Fort Campbell or to some Pendleton, and we say, okay, maybe a study, you're going to be randomly assigned to one of three groups for treatment. We think they all are good. We just want to see if there's a difference. And now we're going to ask you to fill out some questionnaires. We already know from the study we just completed that the trauma symptoms are useless. We have a big study of 1,000 returning troops, pre-deployment, post-deployment. Their CABS tests, their tests on trauma symptoms actually got better pre-deployment to post-deployment, which isn't likely. So what happens is they just won't tell you trauma symptoms. They won't report trauma symptoms. Marines especially will not report trauma symptoms generally. Unless they're going for disability, in which case they'll exaggerate them like crazy.
Right, and they'll never go away.
The way the reason the military intelligence is an oxymoron, because the way the military decides on what kind of disability you're going to get is they put you in an inpatient program, they do therapy. At the end of that time, your disability is determined by how you're doing at the end of that 3 weeks. So if you want to go in and do a study in those groups, all the incentives are for getting worse. Which is
exactly
important. So not a good idea, but anyway. So we know that the CAPS won't give us good numbers, but the combat experiences scale seems to be a pretty valid scale for this group. They don't tend to exaggerate. I mean, if a buddy got killed, a buddy got killed. People won't say that if they didn't. So they're actual experiences that they can quote. And most vets are pretty willing to tell you on a scale what happened to them. So that would be a good covariate here. And the hope would be that it would reduce within group variance. Right? So that we would be able to get a better estimate of how these three therapies worked without something that messes them up by giving more within group variance. Makes sense?
In general, even though it's a covariate, wouldn't it also really help you figure out what exactly is going on?
Yeah, so the correlations themselves are interesting, right? If CES is, that's independent information that's interesting. In fact, if it's not, if the combat experience is not related to your outcome in therapy, that's interesting to know too.
Yeah.
I mean, if you had a therapy that was so powerful that it didn't matter what kind of experiences the person had, but the therapy works the same anyway, that would be very interesting. But remember, if it's not correlated, all you do is lose a degree of freedom. You lose power. So you don't want a covariate that's not correlated.
So for this example, since there'd be different number of traumatic experiences, could you go ahead and group those 1 to 3 group versus? You
can. You can always make another independent variable. So that's one of the options is.
Yeah.
And expand this to low CES. Just make it 2 to high CES. If we're really interested in seeing how therapy works for those 2. But that might cut your sample size in half.
Well, yeah, in theory.
Yeah, so but it might be useful, so that might be a useful one. So that's always a possibility that instead of covariates, you just have another independent variable. It's always an option you might have. But sometimes the other ones are just not interesting. It's like biasing response or something like that. You don't really care about making that an independent variable, whatever that might be. Okay? Get the idea of it? All right. Now it gets a little more complicated to assess the interaction, the assumptions. So I've got a little cheat sheet for you to do it on SPSS. Part of this one, just a part that says testing assumptions. Let's go back through the assumptions again. Let's use this example, because it's a little bit less silly than the other one. I'll show you that one. All right, so in this example, the assumptions are the usual suspects: normality, homogeneity, and independence of observation. And we'll do this again. But the additional ones are linearity of the relationship between CV and the DV. Right? So there you're having DV, remember, which is percentage improvement in trauma symptoms, and CV, in this case, is the CES, combat experience scale. So we want to look at the scatter plot between those two. And the assumption is that the relationship is linear, not curved. Because you're going to miss the relationship if it's curved. So that's pretty easy to assess. It's not often to bring in a curvilinear relationship. You just look at the scatter plot. You can assess that. Okay. Next, the assumption of reliability would just have to do with how reliable that CES scale is. Let's assume we've met that assumption here. The final assumption is a little more complicated. The assumption of homogeneity of regression. This assumption is that if we looked at 3 scatter plots, one for each level of the therapy, and did a CV-DV scatter plot, that the slopes would be approximately equal. Think about it, it makes some sense. If there was a different relationship between combat experiences and trauma symptoms for the support group than there was for these groups, we kind of mess up what we're trying to do, right? We're sort of assuming that whatever that CV is, it has kind of a common relationship to all for each level of the IP. And the consequences of violating that assumption are quite complex. Sometimes it could be type 1 error, sometimes it could be type 2 error, depending on which way it goes. So it is an assumption that we do need to pay attention to. If we violate it very severely, it may be that a COVA is not the appropriate technique to use. Okay?
So is that saying if it would have different effects on exposure, like you would see a different slope for each one of those?
Or for maybe just one of them.
Maybe just one, okay. So,
That would be a violation. Right?
okay. Saying that the combat experience scale
Doesn't correlate with
or nothing
for the support.
for support groups, okay.
And if you don't have random assignment, you can see how easily that could happen, right? If you had, let's say you're comparing, instead of 3 treatments, you're comparing, let's say bulimics, anorexics, obese, and the CV is family health or something. I don't know, let's think about that. What could be a covariate for those 3? Well, weight.
Yeah.
Weight could be, right? So BMI. Well, you know it's going to differ between those 3 groups. And so you can see kind of a mess that if BMI correlates, certainly will correlate with the, we're trying to say that DV was attachment history thing. So let's say weight correlates with attachment history only for the obese and not for the bulimics or something. And that would really mess up our whole stuff.
So would that be where we've basically added we've added degree of freedom, but we've added something that's not correlated?
Well, no, it might be correlated for some parts
For
of it,
some
but,
parts,
but if it's correlated for some and not others, where our conclusions could
Violate,
skew
okay.
one way or the other.
But say one of the treatment conditions worked really well for a higher quantity of traumatic events. Wouldn't that create a different slope? Like say support is better for the
That's what John was saying a minute ago. So then we would want to know, we probably want to redesign the study to have separate groups of CES then. Because
make it an IV instead of
exactly. And then we could actually see how it works for different things.
Okay. That makes sense. All right.
When we're looking at the different slopes on an output, should we look at the plots
Well, I'll show you. I'll show you. But we're going to actually do that's the sheet I just gave you. We're actually going to do a little trick to get that. And then we look at the plots to see what that tells us. This is something we haven't done before, so let me show you that. So what you do is use the same exact program here. General linear model. You can follow along that sheet I just gave you. But we're going to do something a little different than we haven't done. We're going to click Model. And we're going to click Custom. And we're going to put each of the, what it gives you is the factors and covariates, CVs and IVs. We're going to put both of them over. And then we're going to highlight both of them together with the Shift key and put those over as interaction. And then we're going to go to Continue. So what we're going to do is we're going to create an interaction between the IV and the CV. Think about it. If the IV-CV has an interaction, then those slopes won't be parallel anymore, right? So it's just a way of testing parallel slopes. It doesn't tell us anything more than that, but it can tell us if those slopes are parallel. And so that we'll see if they're significantly different than parallel, then we're going to have a violation if they're not significant. Now the thing to remember is the output that you get now is only useful for testing this assumption. Nothing else on the sheet is of any value to you. You can't test the main effects anymore because you're putting in this bunch of other stuff. So once I click Continue, I think I gave it, did I give you the output from that? No, I think I did, yeah. So now you get some new output. Ignore everything else in that output except this line right here.
I don't think we have that.
Those times.
Highlighted, dose by partner. And here we got, it is significant, 0.046. See that? It's on your sheet there.
You don't have
Don't have that one? Did I not give you the three graphs on there too? No, not, it won't be on that sheet. It's on the original, sorry. On the original libido sheet. Remember the data we're using is the libido one. So go back to that first one again.
So we just have a partner and
You don't see the dose by partner in there the second time through? Look again. Flip another
We
page.
don't have a second time through.
Oh, right.
We have plots.
And I did the plots, but I forgot to give you the sheet. All right, so but this is the sheet that I should have given you. And the only thing we care about in this plot, the second sheet I gave is just how to do it in SPSS, is the significance there. So we did get a significant interaction between dose and partner. Now if you do the plots that you got, to get the plots, what you have to do is you go to Data, Split File, and do it by the IV, which is dosage. Remember how we did that before on the first semester? And now I'm going to just do a scatter plot, graphs, legacy graphs, scatter plot, fine. And I'm going to put in the DV, CV into each scatter plot. And that one I did give you apparently. And remember what you do to get the lines is you double click on the graph. And then when it comes up, right click it and do add fit line to total. Click, right click, add fit line to total. Oops, must have missed one. There we go. Right click. Alright, so you can see where the violation is coming from in those three graphs, right? The first two have almost identical slopes. But for the high dose Viagra, it didn't really matter what the partner's libido was. There was no correlation between the partner's libido and their libido. So Ankova was a a little bit of a problem here because of that relationship being kind of messed up.
So first of all, if we found the interaction to not be significant, we'd stop there.
We're good.
Wait, that would be good for us?
That's good.
Okay. And then since it was significant here, we investigated. But how close do these slopes have to be the same? Like where do we cut it off at? Like,
Well,
this is where
you don't have to worry about that because if the significance of the interaction tells you whether it's meaningful or not.
Okay.
So if you have a significant interaction, then you would look at the slopes to see where it's coming from.
Okay.
But you don't have to really test the slopes per se.
Okay.
You can also do that. There's a little test to test the significance of slope differences, but you don't have to in this case. So once you see there's an interaction, now in this case, this would lead us to a little bit of a dilemma because do we really want to use that covariate or not? We didn't run it without the covariate. Let's do that. Okay, so we're just going to run the straight ANOVA. And we'll get another standard output. Oh, split file on. Good. Oh, well, there's the simple effects if you wanted the simple effects, as long as they did them. So, what do we got here? I don't know. I'm going to take the split file off. So this is the ANOVA without the covariate. And we can see we got a way bigger F for, oh no, we got a non-significant F for dose, sorry. 2.46.108. So without controlling for the partner's libido, we didn't get a significant difference between the doses. And the means, this means, look at those two means, they look pretty close to each other. So now you can see you got a little problem here because it looks like for the low dose, the partner's libido made a giant difference. For the high dose, it didn't make much difference. So now you have to kind of decide what you want to do about this. This would probably be one that would be worth controlling the partner, somehow controlling the partner's libido if you possibly could, or splitting it off into some other factors or something like that. So silly example, so it's hard to know what to do with that one. Just as we said there, this does present a problem for us. Now, do we interpret this? Do we interpret that ANCOVA as a significant difference? It looks like it is. Once we control for a partner's libido, it's pretty clear from the graph that the high dose has a pretty powerful effect. And the other two really don't have much difference. We don't know yet whether low dose is actually significantly lower than high dose. We'll do that again. So it's a headache with ANCOVA because if you violate this assumption, you don't exactly know what to do about this. Most people probably would just report this as significant enough with the covariate. Probably tells us what we want to know, but there is some messiness to it because of the violation of the assumption.
If you have this violation, so you can't really use the ANCOVA, would it be better to like look at it from the treatment by blocks or something, or some other
Possibly, but well, in this case, no, it wouldn't be treatment by blocks because it's not severity of the libido that's the issue. It would be doing something about the covariant.
Okay.
So I'd say this would be a sign of a poorly designed study. Because I don't see how you could randomly assign people, unless it was at a brothel or something. How are you going to assign the libido of the partner?
Yeah.
That's a random factor that you don't know about. And it's clearly having a big influence on two of the levels, but not so much on the high level, right? So you end up with some weird stuff.
Seems as though this affects the means. I'm trying to conceptualize in my head how a different slope is going to affect the mean. Is that flat slope going to increase the mean, or is it going to decrease the mean?
Well, in this case, it increased the mean.
In this case, it increased.
Because it took away the cases of some of the cases with low libido, or apparently were dragging down the subject's libido, I guess. I don't actually know, but the mean went up with the ANCOVA compared to the regular mean. So it did heighten the effect, which is probably real, but it is a bit of a problem because we don't know how much type 1 error is built into that just because the assumption is violated. And there's a bunch of complicated ways to try to decide how severe the violation. In this case, it was only 0.046. Even though it looks pretty dramatic in the graphs, it's very few data points. It's probably not enough to ruin it for us. But maybe you need to run more subjects, or maybe you need to redesign the study or something. Okay. So those are the assumptions. The other one we didn't really deal with is reliability of the covariate, and you can always do that by at least looking at internal consistency or something of it. But honestly, people ignore that reliability assumption pretty regularly. It's not as powerful as the homogeneity of regression. That is pretty important. So you have to kind of come up with sort of a decision tree of what to do in those situations. We'll put together later in the semester. Now, the one final thing is, what if we wanted to compare our placebo to our low dose, including the covariate? Well, let's say without the covariate, how do we do it? How do we do it last semester? If I wanted to just go in and compare low dose to placebo on a one-way ANOVA, how do we do that in SPSS last semester?
We would compare group 0 compared to group 1.
Yeah, so we'd go in to compare means, right? That first non-module compare means, not general linear model. And we would do 1, -1, 0. Remember? For the three groups, 1, -1, 0 would be the placebo, low dose, high dose. So that would get us the comparison just between the placebo and low dose. Right? Trouble with that is that there's no place for covariates in that analysis. So you have to figure out a way of using general linear model to do this. And actually, when we did it the first time, we're going to dummy code these guys into some codes that allow us to do that and still use the covariate. So here's the way Andy Fields likes to do that. He created a new file with the dose. Here's the dose code here, but here's a couple of dummy codes. This one is coding -2 for the first group, that's placebo, and then 1 for the other group. So that would be a way of getting a comparison between the combination of these two versus this one. Which I don't really think we care about so much, but we might be able to do that one. Very dummy coded. First group is 0, and everybody else as a 1. Now that's comparing the first group to everybody else as a -1. You can use that. You could use that as any code you want in there. We probably, to do the code we want, we would probably want to do just use our same idea when we do that. 1, 1, 1, 1, 1, 1. And then we could use a -1 or something if we wanted to for the next ones. Oops. This one. Along there. far enough.
I think you're 1 over.
1.2. Okay, so now if I run my analysis,
One more. That's 18 and 19.
and I'm going to do the analysis, so I'll do Vito as a DB. I'm not going to use dose, I'm going to use my dummy code as a fixed factor. I'm going to still put in partners libido as a CP. Same options. It's important that you put the means over in this one, otherwise you don't get the adjusted means. Okay, so here we get variable 1 is our independent variable. Covariate is highly significant, and we still get a significant difference between 1 and 2. I would have thought it wasn't so significant, but I guess it was. Let's see if the means make sense to us. First group was 3.02, the second group was 4.869. So there's quite a bit of difference between those. So now that's with the covariate in there. And then if we tested the assumption here, we're pretty sure we're going to not violate the assumption, right? Those two slopes we know already are pretty similar. So let's just do it. So that would be, now I'll put in model, custom. No significant interaction. We kind of knew that already, but so that means for that comparison, we met the assumptions nicely. So you can't. So the trick is you can't do it any other way if you want to get those particulars. You've got to use this trick, some kind of dummy coding trick to do it. You can use a number of different codes for that. All right, does everybody get how to do the models thing? We gave you a little snag to see how to do it. Because you have to do that in the homework. And remember, the most common mistake is people get the second output from the assumption, and they interpret that as the meaning of the original one. And it doesn't mean anything except for that interaction. All you care about is the interaction of the second output. When you run through for the assumption, just look at the interaction. If it's not significant, you're in like Flynn. If it's significant, you got to go back and figure out where it's coming from.
Because if the interaction is not significant, then your assumptions aren't violated.
The assumption of homogeneity of regression.
Okay.
You don't know about linearity or homogeneity of variance, or in this case, I noticed that he had a violation of homogeneity of variance too. Remember from the original output, which means we better. Now that one is pretty robust a violation. We'll probably ignore it, but we should probably look and see where it's coming from. Here's the standard deviations of the original data. The high dose had quite a larger standard deviation, so if we squared that one, it would be 4 for the variance, and this one would be, I don't know, 3, but it must just barely be significant. Doesn't look very different. So remember our F maxes need to be pretty big for us to worry about homogeneity variance. It's a pretty small sample, so probably have to ignore homogeneity variance violation in this one and worry more about the other assumption. And then the other reason that static group designs are a problem is that you're almost always going to violate that assumption in static group design, right? You have 3 separate groups of people. And CV, DV is just not likely to be the same correlation for each group of persons, right? So let's say we had, let's see if we can think of another example of this. Let's say we had let's say we're going to compare deployed troops who were in the Kurdish region of Iraq, which turned out to be very safe and not very many combat experiences, versus in Fallujah. And we wanted to use that somehow as a comparison. Well, those troops are very different troops. And they have very different experiences. They have very different backgrounds, probably. There might be more National Guard in one than the other. Now you say, okay, well, I'm going to control for all that with covariates. Well, how many covariates can you have? And how many covariates you can put in there? And are they going to really work to do this? And you're always going to have a bit of a mess when you have static group designs. But it may be something that you still need to study, so you just have to do your best to kind of do it. The bottom line is treat it like it's a correlation, not like a random control trial. So you've got an association between being in the north of, let's say, being in the north of Iraq and something happening to them or something, some outcome. You wouldn't want to say there's a significant difference. You could say there's a significant difference, but the interpretation of the significant difference is more like a correlation. It tended to be people in this region had more of something than the other, rather than like you would do from a random control trial. And the same thing is true if you, one of our long retired faculty was a research design teacher, and his hobby now is to go through the newspaper and criticize all these epidemiological studies that show you that red meat is good for you, red meat is bad for you. So, I mean, those studies are really iffy because you just can't control for everything. So recently there was a big study showing, especially processed meats were just death. And the amount of processed meat that you eat is just way shortens your life. Well, if you go through and really carefully control for all the factors in that, because they didn't control for vegetarians, and so the vegetarians had very little processed factor, but they were health nuts, right? The people who eat salami sandwiches every day are not health nuts. They eat a lot of junk food. That turned out to be the big thing that created the mortality differences, not the diet itself at all, but a lot of other factors. So there's always a million of these things you got to be really careful of, even if they try and control for them.
Do covariates always have to be on like an interval or ratio scale, or can they be categories?
They can be category, but if they're category, it ends up being like another IP, sort of. So you can put them in as a category if you can see them if you want to.
So if some theoretical study, my covariate could be, say I'm doing some like running thing, my covariate could be like type of shoe, like running shoe, boot.
You can't put, you can't put them because you couldn't code those 1, 2, 3, 4, 5. So you have to dummy code those as separate ones. So if it's natural shoes, for the different kinds of shoes are in different categories, each one would have to be a 1, 0 as a separate CV.
So maybe I would have to do something like weight of shoe instead of like category.
Yeah.
Okay.
But let's say you wanted to do merit status, just merit, not merit. Well, you can put that in as a CV 1, 0. But easier way to do that is just use that as an independent variable, make sure it doesn't matter. Right? So you kind of get those potential covariates. The other thing we often see is that, final thing real quick, if you're doing a study, a treatment outcome study, so many of you will do of some kind, you're going to try to do something that one group and the control group doesn't get it. And you're doing your group equivalents, and you have a whole bunch of data on all these people. Paul's study, so some of these guys are running a study with it. One of our students is looking at 2 different kinds of biofeedback and their effect on brain waves. So, and it's completely randomly assigned, but when you get done, you've got age and BMI and what else we got? We've got a whole demographic sheet of variables. So the first thing she'll do is analyze the group equivalents, right? So you use t-tests for continuous measures and chi-squares for category measures. And you're hoping that your randomization worked, that the groups are not different, but out of all of those, something's likely to be different, right? So now the knee-jerk reflex is to use it as a covariate. But you don't have to do that unless it correlates with the pre-post differences. Right? Just because there's a difference between the 2 groups, if it doesn't matter in terms of their brainwave measure that we're doing, then you don't have to use it as a covariate, only if it really does influence the outcomes. So So you would right away test that to see. And if it does influence it, then you got another headache. Okie doke. That's all we're going to do in COVA. We'll review it again later.
I know a lot of people are having trouble, I don't know if this class is, but I've talked to the other class about the homework that's due tomorrow.
Did they?
Chapter 16, if people couldn't get it up or something, they're having a lot of trouble.
That's the one. That's not the one.
I didn't even try, no. That was last week's.
What's the problem with that one? That's an Amos one?
Yeah, they weren't able to get the information.
You can't get it to work on computers, is what you're saying? Yes. You don't know? Anybody get it to work? Somebody try it?
I think
What happens? You just can't get Amos?
They can't get, like, the data file will come up.
Okay, so you have to load that data file in SPSS first. And you can get the data file in SPSS?
Yeah.
Okay, then when you go to Amos, what happens?
you have to load the file.
The file will load. I know the other class literally just canceled that part of it, so it wasn't working. Goldenberg just canceled it.
Just cancel that homework. So that, what we're supposed to do is a SCM? Is that an SCM?
Yeah.
So
Basically, straight up English.
I wonder if it's just a mistake in getting it.
Chapter was it?
So it actually loads in the,
Which one was it?
SPS.
It doesn't load at all.
It doesn't load at all. Oh, okay. Well, if you can't do it, you
But
can't
someone
do
might have been able to figure it out.
it. It doesn't sound like anybody has so far. So was there a substitute we can use for that one? Last year, maybe?
No, because they use the same problems they do last
Oh,
year.
that's
It's the same data set.
It's a double homework thing. But that's the only one for us.
Yeah, well, forget it then. If you can't do it, you can't do it. We'll try to work on it. We'll have a little bit of time left. We'll do another SEM sometime later this semester.
So we don't need to do the homework?
Yeah, well, I guess if you can't do it, I mean, what are you gonna do? I haven't tried to load that data, but if you can't get
It's
that
the one-
data to load in the first place, then you
Is
can't
the
do
one
it.
due today? Or for the next week?
That was due tomorrow.
Yeah, tomorrow. Okay.
I know I usually have trouble getting stuff up with the entire other class, but all their stuff is due today and none of them could do it either.
Okay.
So that's,
Okay, well, good. Thanks for pointing it out. I didn't know that.
So we cancel.
So we did one with the confirmatory already, right? You guys were able to do that. Yeah. So we'll spend a little time later in SEM. We're a little bit ahead of the class. We'll go back through and do some SEM. So we wanted to re-go over identified, under identified, reproduce. We'll do a little bit of that later in the semester. I think we have some time. We'll do that. So you're off the hook for this one.
So just the chapter 12 assignment for each one?
Chapter 12 is a different one, right?
Right.
And then the one for next week would be 16, or was that?
No, there were two of them.
Oh, the two of them, yeah, so just do chapter 12. Right, that's plenty to do anyway. But just make sure that you practice enough with the confirmatory so you know how to do all the mechanics of it.
So we have
It
chapter.
takes forever to learn how
12.
to do that. But I mean, on the other hand, you guys did great on the output. Amos output, that was by far better than the factor analysis output. Which I thought it was going to be the opposite, so shows what I know. Okay, well, thanks for pointing that out. Everybody get that? So just chapter 12, not chapter 16.
Okay.
We'll try to get another data set for you for 16. What was that data set about in 16? Do you remember? Yeah, what did we have?
I don't know if they just something up online or.
It must have been, they just corrupted the file or something. So. But I need to find another file, so I'll do that later in the semester. Even if we just do it, maybe we'll just do it all together in class instead of the homework. Maybe that's a good way to do it. So everybody can learn.